look at a couple of things, right? Let's just kind of discuss some ideas. Let's determine whether the distance described is an increasing distance or a decreasing distance. So we're looking at distance. That's the important thing to remember in this question is what are we describing? We're describing distance. Is it increasing or decreasing? So we're looking at the distance from school as we're driving from home to school. So if we're starting at home and we're driving to the school, the distance from the school is as we're driving from home to school, we're getting closer and closer and closer to the school. So the distance from the school is getting smaller and smaller and smaller. So we would say that the distance is decreasing because it's getting smaller as we get closer to it. What about if we're driving from school to the home? So the distance from the school to the school is 0, but as we start driving home, that distance starts to increase. It would be increasing. What about if she stops jogging and she's not moving anymore? She's completely at rest, but she was jogging. So she went from jogging to resting, so that's going to be a decreasing on our heart rate. All right, now I want you to go ahead and turn to page 200, which is the beginning of section 5.4 using graph in your BJU Press Algebra 1 textbook. And we're going to take a look at the growth of a largemouth bass. So a bass is a type of fish. It's a largemouth, so it has a huge mouth. You can actually look at the picture on page 200. And we are looking at the growth, okay? So since we're looking at the growth, we're looking at how old the bass is and the length of the bass, right? So we have to decide which one is dependent on the other. Well, age, it doesn't matter what the length is. That's not going to tell you how old they are. However, the age could tell you how long they are. So age is independent because it doesn't depend on anything. The age is the independent variable. So we would put that on the x-axis or the horizontal axis. And the length depends on the age. So length is the dependent variable, and remember dependent is your y-axis or your vertical axis. So this is a chart that's on page 200. So they've already put in this data for us. So notice that age is on the x or the horizontal and length is on the y or the vertical. So it went ahead and plotted the data. This is what we call a scatter plot. It's a bunch of plotted points, right? So they plotted the points for us, which was great. And so now what we can do is we can actually go ahead and sketch a smooth curve connecting those points, okay? So we're going to connect points with a smooth curve. And what that does is that allows us to approximate different information. Like, for example, we knew the exact approximate length at 1 year of age was 6.5. And we knew the exact length when it was 2 years old. But what about when it was 1.5? How long was it then? Well, we can use our smooth curve to approximate that answer, which is so neat. Like now we can actually approximate. We can also make predictions based on if we were to continue that curve and where it was going, right? So, this process of graphing data and to find the shape of the data, okay, so studying the shape of distribution, we call that mathematical modeling. So the purpose of doing a mathematical model is to illustrate an idea and make it easier to comprehend. So we're looking at the data and we're comprehending it, we're digesting it and getting the information that we need from it. So what I'm going to go ahead and do now is I want to look at example 1 in your textbook on page 201. So we're looking at postage, the price of postage stamps, okay? So they give us some tables and it has years and it has the cost of a stamp in cents, right? So the year is unaffected by the price. So the year is independent or your x, and that means it's on the horizontal axis. And the price depends on the year, so that's going to be the dependent variable. It's going to be graphed on the y-axis or the vertical axis. And there's a picture on page 201, and you can see that, you know, they plotted the points, right? And notice how they had to, they didn't start at 0, like year 0, then year 1, and then year 2. They went ahead and they started with 1850, and then they went up by 25, so that way that the graph looked a little bit neater, right? And then stamped cost was in cents, and then it went to 0 to 100. So looking at that, they plotted the points, and we can look at that and say, wow, like for a long time, the stamps stayed the same. There was no increase, right? However, and around year 1975, there was like a huge jump, and so they started to increase dramatically since 1975, or in most recent years. Okay, we can also make predictions. How do we make a prediction? Well, we're going to draw a smooth curve that connects all of those points, and then we show the general shape of the distribution over the time period. And so based on where the points are going, if it continues in the way that the shape is, by 2050, it would cost about 80 cents to mail a letter. Okay, so what we did just then is we interpreted that data and made a prediction. So let's go ahead and look at example 2 now. In example 2, we're looking at a skydiver, and we're looking at the distance fallen versus time. So distance is going to be dependent on time. So time goes on the horizontal and distance goes on the vertical. And so what we're looking at is the distance he fell at what time. So at T1, at T0, at 0 seconds, he hasn't fallen, so it's at 0. But after 5 seconds, he's already fallen 500 feet, and then so on and so on. So let's answer some questions. At 10 seconds, how many feet has he fallen? Well, at 10 seconds, he's fallen about 1,300 feet. And then what about at 14 seconds? Well, actually, let's look at it backwards. How long does it take to fall 2,000 feet? Well, at 2,000 feet, it's going to take about 14 seconds. It's a little less than 15. So you can go both ways on that. You can answer 2 different types of questions. Let's look at another question. What about, let's describe the fall of the skydiver in the first 5 seconds, and then the next 15, and then the final 10 seconds. So in the first 5 seconds, it's a greater distance, right? Because he's falling, right? And then each seconds after that, it gets more and more. And then he falls at a much slower constant rate during the last 10 seconds because that's when he's getting closer to the ground. All right, let's take a look at graphs without numbered axes. So these kinds of graphs are just doing a description. There's no actual numbers. You're just describing what is happening, okay? So they're doing relative. So here, this is relative speeds versus time, okay? So as the time increases, speed is increasing, and then at a certain part, the speed stays the same, and then it decreases, and then it levels out again. So this is describing something. Okay, let's take a look at example number 3, which is found on page 203. What we're looking at is we're looking at a graph of mountain hiking, and it looks like we're comparing time to the heart rate, and then we're also looking at the same time, but instead of comparing it to heart rate, we're comparing it to altitude. So we're looking at a graph that does not have numbered axes on there. It's just illustrating the relationship between the variables. So the question is that what is happening in between each interval of time? For example, the interval A, it looks like you increased suddenly on the heart rate and then you stayed steady. And that's also on the altitude on section A in time. The altitude was increasing steadily as well. So in A, or the time segment A, we could say her heart rate is elevated as they ascend the first slope of the mountain. And then you get into section B. If you notice in section B, the heart rate decreases in a steady, and the altitude in section B is completely steady as well. So her heart rate returns to normal where they're at the top of the mountain and they're not climbing anymore. And then in section C of time, it looks like her heart rate goes slightly up as well as they walk partway down the mountain. So you notice that they're going down the mountain, so the altitude is decreasing, but her heart rate is only increasing a little bit because she's climbing down, she's not climbing up. And then in the section time of D, her heart rate is elevating greatly because she's climbing a really super steep slope, because if you notice, the altitude is way higher than any of the other altitudes. And then part E, again, she's at the top of another mountain, so her heart rate is back to normal and the altitude hasn't increased at all. And then the last segment of time, segment F, it's when she's going down the mountain, so her heart rate remains slightly elevated, but it's no longer increasing anymore because she's going down the mountain, she's losing all altitude, and so it's not as hard for her heart rate. All right, go ahead and try some problems on your own.